Good afternoon, everyone. We'll be starting with the next session, first session for the electromagnetic induction, right? So in this session, we'll be discussing the previous year questions only, right? So in your exams, at least one or two questions are asked from this chapter, right? From electromagnetic induction. So we'll be beginning with the question related to transformer, right? Question related to transformer. So we know that in case of transformer, we have two coils. One is the primary coil and one is the secondary coil, right? Primary coil is actually the source of the power, right? And the same power gets distributed or supplied to the secondary coil, right? And let's suppose that this is the primary coil, right? This is the primary coil. And let's suppose N1 turns are there in primary coil and V1 is the voltage supplied to the primary coil, right? Then we have the secondary coil here, right? And let's suppose N2 are the number of turns in the secondary coil and V2 is the voltage across the load or across the secondary coil, right? So due to mutual induction, there is an induced EMF in the secondary coil because of the change in the or supply of the voltage or supply of the AC to the primary coil, right? So the ratio of the voltage between the secondary coil and the primary coil depends upon the number of turns in the primary coil and the secondary coil, right? So V2 upon V1 will always be equal to the number of turns in the secondary coil, right? Divided by the number of turns in the primary coil, right? So V2 upon V1 is always equal to N2 upon N1, right? And similarly, we know there is a constant source of power, right? Whatever power is supplied by the primary coils, same amount of power will be ideally absorbed by the secondary coil as well, right? So it means that I2 upon I1 will always be equal to N1 upon N2, right? N1 upon N2. So these are the two primary equations we study in case of transformer, right? That's the ratio of the voltage across primary and the secondary coil, right? And the ratio of the current flowing through the secondary and the primary coil, right? So it is N2 upon N1 for the V2 ratio between the voltage of secondary and the primary coil, and ratio between the currents of the secondary and the primary coil is N1 upon N2, where N1 is the number of coils in primary coil, right? This is a primary coil and this is the secondary coil, right? Secondary coil, right? The question is about a transformer has an efficiency of 80%, right? It works at 10 volt and 4 kilowatt, right? If the secondary voltage is 240 volt, then the current in the secondary coil is, right? The efficiency, we define efficiency of any source as it's the output divided by the input. Now here output is the power through the secondary coil. We'll write it as output power divided by input power multiplied by the vector of 100, right? Vector of 100, right? So you can see here the efficiency is given as 80%, or we can write it as 0.8, 0.8, right? Or we can, since we have multiplied it with the 100 here, we can write it as 80, right? Eta is 80. So 80% is the efficiency. That's equal to output power upon the input power. Let's suppose the output power will be the voltage across the secondary coil multiplied by the current flowing through the secondary coil, right? We can write it as V2 multiplied by I2 upon the input power. Now you can see maximum input power that the primary source can supply is the 4 kilowatts, right? So P input that's given by the primary source, that is 4 kilowatt, or we can write it as 4000 watts, right? So this is the power supplied by the primary source, right? So if the secondary voltage is 240 volt, right? The second voltage of the secondary coil is given as 240 volts. It means V2 is given as 240 volts, right? We have to find the current through the secondary coil, right? So input power is 4000, right? We'll write here it as 4000 multiplied by 100. So V2 is given as 240. So it will be 240 upon 4000 multiplied by I2 multiplied by 100, right? So this and this will get cancelled. This will also get cancelled. It will be 4, 6, right? So from here, the value of I2 comes out to be equal to, it will be 80 upon 6, or we can write it as 40 upon 3. That will be equal to 113 will be left with 10. It will be 3 0.3, right? So it means that 13.3 amperes will be the current flowing through the secondary coil, right? So 13.3 amperes will be the current flowing through the secondary coil. So these two equations are very important. Three equations that I will be mentioning here with respect to the transformer that are very important, right? The first equation is the ratio between the voltage across. We can write it as we can write it as Vs, that's the voltage across secondary, upon Vp, that's the voltage across the primary. So it depends upon number of turns in the secondary coil divided by the number of turns in the primary coil. So this is the first equation that you need to remember with respect to a transformer. Transformer is a very important question with respect to a competitive exam, right? And similarly about the ratio of current through secondary and the primary, that's Is upon Ip. So it will depend upon the number of turns in primary, that's Np upon Ns, right? Np upon Ns. This is the second equation, which is very important, right? Which is very important, right? Now this equation is applied when there is a 100%, we can say 100% efficiency, or we can say for an ideal transformer, right? Ideal transformer or 100% efficiency, right? Ideal transformer or for 100% efficiency. And when there is efficiency less than the 100 or less than 1, then we use the concept of the efficiency, that's the output power upon the input power. That efficiency eta is nothing, it's the P output upon P input, right? Multiplied by 100, right? So P output will be nothing, it will be the voltage across secondary and current across secondary multiplied by 100, right? Divided by voltage across primary and current across primary, right? So this will be the efficiency, right? So this equation we can use. These three equations are very important equations with respect to your transformer, right? So we can use these three equations to solve any question with respect to transformer asked in your competitive exams, right? Now let's move on to the another question, right? Another question number two. The question number two is, a coil is placed perpendicular to a magnetic field of 5000 Tesla. When the field is changed to 3000 Tesla in 2 seconds, an induced EMF of 22 volt is produced in the coil, right? If the diameter of the coil is 0.02 meter, then the number of turns in the coil is, right? We have to find the number of turns in the coil, right? Now we know that the induced EMF is nothing. It's given as minus d phi over dt, right? According to Faraday's law, right? Where phi is nothing, is the flux, right? Phi is nothing, flux. So if the flux changes through the coil, right, then the EMF will be induced through the coil, right? So now let's try to calculate the flux through the coil, right? We know that for a uniform magnetic field, or the flux is nothing, it's equal to P dot A, right? It's P dot A. This is the flux, right? And since coil is placed perpendicular to magnetic field, right, it means that the area vector will be along the direction of the magnetic field vector. It means that we can write this flux as B multiplied by A only, right? B into A. Now there is a possibility there is a possibility, since the question asks about the number of turns in the coil, it means that there must be some n number of turns in this coil, right? So the total flux will be, it will be nothing, it will be NBA, right? NBA, where N is the total number of turns in this coil, right? Now the magnetic field is given as 5000 Tesla, right? The diameter is given as 0.02 meter, right? So we can write it as N is the number of turns in the coil, magnetic field is 5000 Tesla. Diameter will be, that's given as 0.02 meter, and the area will be pi r square, right? So pi r square, we can write it as pi d square upon 4, right? Pi d square upon 4, right? Where d is the diameter, right? So we can rewrite it as 5000, right? Pi d square. Now the value of d is given as 0.02 meter, right? Or we can write it as 10 to the power minus 2 meters, right? 2 into 10 to the power minus 2 meters. That will be 4 here. That will be 10 to the power minus 4 here, right? Divided by 4, right? So 4 and 4 will get cancelled. So we'll be left with, it will be 5 into 10 to the power minus 3, right? Minus 1. So it will be n into 5 multiplied by pi multiplied by 10 to the power minus 1, right? So this will be the flux, right? This will be the flux. Now, the question is that when the field is changed to uh, 3000 Tesla in 2 seconds. It means that the flux has now changed. Now the final, this was the initial flux, right? Now the final flux will be, it will be N multiplied by, we just have to change the magnetic field to 3000 Tesla. We will have a factor of 3 here, right? 3 multiplied by pi here into 10 to the power minus 1, right? Into 10 to the power minus 1. So this will be the final flux, right? This will be the final flux. So from here, the change in flux will be nothing. That will be 5 minus 3 will be 2. It will be 2 multiplied by n, right? Multiplied by pi upon 10, or we can write it as n pi upon 5, right? N pi upon 5. So this will be the change in flux. This will be the change in flux, right? So this flux has changed in a time of 2 seconds, right? In 2 seconds, this much of flux has changed, and the induced EMF was 22 volts. So the induced EMF is 22 volts, and the flux has changed by n pi upon 5, right? Divided by the factor, the time in 2 seconds. So we'll divide it by 2 seconds. So it will be n pi upon 10, right? So the value of n here will be nothing. It will be 22 multiplied by 10 upon pi. So this will be the number of turns in this coil, right? So we calculated the number of turns in this coil, right? So the basic equation we used here was the Faraday's law, right? According to Faraday's law, the induced EMF is nothing. It's the change in flux, right? Per unit time, right? Whatever be the change in flux per unit time will be the induced EMF through a conductor, right? So induced EMF is nothing, that's minus d5 upon dt, and the direction of current is induced EMF, or the induced current is in such a way so that it always opposes the change, or it always opposes the change in flux, right? So that's the importance of this negative sign here, right? So that's what we call as the Lenz law. So Lenz law actually gives us the direction of the induced current, right, in a system. Now let's move on to this question number 3, right? You can see here in the question number 3, we have the match the column type questions, right? It's these are the match the column types questions. So we have list 1 and the list 2, right? In the list 1, we have been given the names of certain laws, right? And we have to find out the correct equations for those certain laws, right? The first in the option A, we have been given as Gauss law of magnetostatics, right? So the Gauss law of magnetostatics is nothing. It's the flux through the closed surface. Magnetic flux through the closed surface is nothing. It's always equal to 0, right? So the magnetic flux through the closed surface is always equal to 0. That's integral of B dot ds is equal to 0. And this signifies that the magnetic monopoles does not actually exist, right? So magnetic monopoles do not exist. So this is the Gauss law of magnetostatics. So A will be second, right? Faraday's law of electromagnetic induction is nothing. That is integral of that's induced EMF is nothing. That's equal to minus d5 over dt, right? d5 over dt, right? So induced EMF, we can write it as integral of E dot dl, right? E dot dl. That will be equal to, even if we find this in a closed loop, that will be still equal to minus d over dt of flex. We can write it as p dot da, right? P dot da. P dot da. Like from here, you can see here this equation correctly represents the Faraday's law of electromagnetic induction. And we know for a conservative field, the closed line integral of the electric field is always equal to 0. But you can see here it's non-zero here. It means the electric field induced because of the change in flux, right? It's actually a non-conservative field, right? It's a non-conservative field, right? And the electric field due to static charge, those are the conservative fields actually, right? So the electric field induced because of the change in EMF, it's actually a non-conservative field, right? So option B will correctly match to the third option of the second list, right? Gauss law of electrostatics. So Gauss law of electrostatics is nothing. Gauss law of electrostatics is nothing. It's the total electric flux through a closed surface is nothing. It's the charge enclosed upon the epsilon naught, right? Upon the epsilon naught. Now let's suppose there is some volume charge density rho, right? Volume charge density rho. Then the total charge enclosed in some object having the volume charge density rho is nothing. It's the integral of volume integral of this charge density. We can write it as rho d tau, right, or rho dv, right? So this integral we can write it as integral of rho dv upon epsilon naught, right? So the correct representation of this Gauss law is option one, right? Option one. So D option matches with the option one, right? Now the Ampere's law. Ampere's law is nothing. It's the line integral of closed line integral of magnetic field will always be equal to mu naught I enclosed, right? Mu naught I enclosed. So this is the correct match, right? For option A, we will have. So A will be correctly matched with second, right? And B will be correctly matched with third, and the C will be correctly matched with fourth, and the D is correctly matched with 1, right? So this is the correct order for the match the following list, right? So this is the final answer, right? Now let's move on to the another question, right? A rectangular loop of length 2.5 meter, right? A rectangular loop of length 2.5 meter with width 2 meter is placed at 60 degree to a magnetic field, right? So the question has been given as we have a rectangular loop of length 2.5 meter and width 2 meters placed at 60 degree to a magnetic field of 4 Tesla. The loop is removed from the field in 10 seconds. The average EMF induced in the loop during this time is. So the average EMF will be nothing. Average EMF will be nothing. It will be actually equal to whatever be the change in flux upon the uh, time delta t, right, upon the time delta t. So delta t has been given here as that's equal to 10 seconds. Now we have to find the change in the magnetic flux route. So initially the flux linked with this loop will be given by p dot a, right? That's p dot a. That's the dot product between the magnetic field vector and the area vector. And it is given that the loop is placed at 60 degree to a magnetic field. It means the angle between the magnetic field and the area vector is 60 degree here, right? So we can write here it as PA cos 60, PA cos 60. Now the value of B is given as 4 Tesla and the area will be 2.5 multiplied by 2, right? Divided by 2, right? Cos 60 is 1 upon 2. So we'll be having here initial flux that will be value 10, right? 10 will be the value of the flux, that's 10 Tesla meter square, right? 10 Tesla meter square. So this will be the initial value of the flux, right? Now, once the loop is removed from this, once the loop is removed from the field in 10 seconds, right? The final flux will be zero, right? Final flux will be zero. Now, the change in flux will be nothing. The average induced EMF will be nothing. It will be minus delta phi upon delta t, right? Now you can see here, delta phi is final minus initial, that's 0 minus 10 upon the delta time, that's 10 seconds, right? So it will be a plus 10 upon 10, that will be equal to plus 1 volt. So plus 1 volt will be the induced EMF, right? Plus 1 volt will be the average induced EMF during this time in a loop, right? So let's move on to the question number 4. Talking about the question number 4, 12 volt battery connected to a coil of resistance 6 ohm, right? A 12-volt battery connected to a coil of resistance 6 ohm through a switch drives a constant current in the circuit, right? The switch is opened in 1 milliseconds, right? So question number 4 says that 12-volt battery connected to a coil of resistance 6 ohm, right? Through a switch drives a constant current in the circuit. The switch is opened in 1 millisecond. The EMF induced across the coil is 20 volt. The inductance of the coil is, right? So we have to find the self-inductance or inductance value of this coil, right? So we know that whenever we have an inductor, right, the induced EMF or the current flowing, the induced EMF in this coil is L be the inductance of this inductor. So E is nothing, it's minus L di by dt, right? So this is the induced EMF in this coil, right? It's given that the induced EMF across the coil is given as 20 volts, right? 20 volt is the induced EMF, right? The switch is opened in time delta t, right? Delta t time is given as 1 millisecond, right? 1 millisecond is given as the delta t time, right? And now it's given that 12-volt battery connected to a coil of resistance 6 ohm through a switch drives a current, a constant current, right, in the circuit, right? Okay. A constant current in the circuit. The switch is opened in 1 millisecond, right? Is opened in 1 millisecond. Okay. The EMF induced across the coil is given as 20 volt, right? That's given as 20 volt. Uh, the inductance of the coil is, right? We have to find the inductance of the coil, right? So EMF induced in this coil is actually 20 volts, right? 20 volts, right? Now let's suppose if this is connected to a battery, right? This is connected to the battery, right? This is connected to the battery of this is connected to a battery of 20 volt, 12 volts, right? 12 volts, right? Now we can apply the Kirchhoff's law in this circuit as well, right? The resistance of this coil is given as 6 ohm, right? 6 ohm, right? So applying the Kirchhoff's law for this circuit, it will be, let's suppose V is the battery voltage supplied by this battery, that is V minus L di by dt. It has to be equal to 0, right? It has to be equal to 0, right? So it means that V must be equal to L di by dt, right? V must be equal to L di by dt, right? For this circuit, right? So we have to find the current, we have to find the inductance of this coil, right? We have to find the inductance of this coil, right? The resistance is given here. The resistance is given as 6 ohm, right? Resistance is given as 6 ohm, right? R is given here as 6 ohm. That's the resistance of this coil, right? That's the resistance of this coil, right? We know that the resistance of the coil, it depends upon the frequency as well, right? So we cannot use that concept here, right, to calculate the inductance of the coil, right? So EMF is given as induced EMF is 20 volts, right? 20 volts, but this V should be equal to L di by dt, right? It should be equal to L di by dt, right? So if V is equal to L di by dt, now the concept of we have to calculate the current, right? We have to calculate the current through the circuit, right? So the value of current here in this circuit will be the current through the circuit will be I, right? That will be delta I, whatever will be the change in current. Let's suppose that's delta I. That will be induced EMF, that is delta E upon R, right? So this will be the current through this circuit, right? I. So delta I here will be induced EMF is given as that's 20 volts, right? 20 volts upon the resistance, right? 20 volts upon the resistance. So resistance here in this circuit is uh, that's 6 ohm, right? So 20 upon 6 will be the 20 upon 6 ampere will be the current through the inductor, right? 20 upon 6 will be the current through the inductor, right? If this much of the current is through the inductor, so this current is actually generated in a time delta t equal to 1 millisecond, right? So 20 volts is the EMF, right? It will be L delta I, that's given as 20 upon 6, right? Multiplied with the time t, that's 1 millisecond, that will be 10 to the power minus 3, right? So from here, 20 will get cancelled, and the value of L comes out to be equal to it will be 6 into 10 to the power 3 Henry, right? So this much of inductance has to be there, right? This much of inductance will be there for this coil. If in 1 millisecond, 20 volts of the EMF is induced across the coil, right? Now let's move on to the question number 5. An EMF of 0.08 volt is induced in a metal rod of length 10 centimeter held normal to a uniform magnetic field of 0.4 Tesla when moves with a velocity of, right? We have to find the velocity of this wire, right? We have to find the velocity of this rod. We know that whenever magnetic field, whenever a metallic object or an object conductor moves in a uniform magnetic field, right, or in a non-uniform magnetic field as well, then EMF is induced, right? That is what we call as the motional EMF, right? And the EMF induced is nothing; it's actually given by integral of V cross B dot dl, right? V cross B dot dl, right? Dot dl. Now, if the magnetic field is perpendicular to the velocity vector, right, then sine 90 will be equal to 1, right? So it will be, and the V cross B will be along the direction of dl vector, right? In that case, the magnetic field or the EMF induced will be nothing. It will be BBL, right? BBL will be the induced magnetic field, right? So that will be induced EMF, not magnetic field, right? So an EMF induced here is actually induced EMF is given as 0.08 volt, right? in a metal rod of length that's given as 10 centimeter, that will be 0.1 meter, right? Held normal to a uniform magnetic field. Given that it's held normal to a uniform magnetic field, the angle theta has to be here 90 degree, right? So B value is given as 0.4 Tesla, right? Now we have to find the speed. So we can just use this equation 0.08. That will be B. That will be 0.4 into V. We have to calculate, and the length 0.1, right? So it has to be actually, so it will be actually equal to 0.04, right, into V, and 0.08, right? 0.08 divided by 0.04, it will be 2 here, right? It will be 2. So V has to be equal to 2 meter per second, right? So 2 meter per second will be the velocity of this rod, right, with which it must be moving, so that 0.08 volt of EMF is induced through the length of this rod, right? Through the length of this rod. Now let's move on to the another question. A metallic rod of length L is rotated with an angular speed of omega, normal to a uniform magnetic field P, about an axis passing through one end of rod, right? Now, the question is that we have a metallic rod, right? Just the metallic rod, and the length of this metallic rod is L, right? And now you can see here, this metallic rod is rotated with an angular speed of omega, normal to a uniform magnetic field, right? There is some magnetic field, normal, uniform magnetic field, normal to this, right? And in this magnetic field, this metallic rod is actually rotated, right? In this magnetic field, the metallic rod is actually rotated, right? So there is a magnetic field. In this magnetic field, the metallic rod is actually rotated, right? And the angle of rotation of this angle of rotation, or the speed of rotation of this metallic rod along this axis is given as to be omega, right? Omega is the rotation, right? Omega is the rotation. Now L is the length of this rod. Now there will be some induced EMF, right? There will be some induced EMF in this rod, right? Now let's suppose at a distance of x from this axis, right? At a distance of x, we have an element dx here, right? Dx. Then there will be some small induced EMF through this element, right? That will be actually BVDX. BVDX. This will be the EMF induced in this element, right? BVDX will be the induced EMF through this elemental length dx, right? Now it's moving with an angular velocity of omega, because at for we know in case of rotations, the angular velocity of each and every point on the rod will be same, but the linear velocity will be different because of the different circumference of the circle that each of the particle will follow, right? Now we can use this equation. V will be equal to r omega, right? Now for this particular element, the V will be equal to x omega. We can substitute the value of V as x omega. So dE here has to be equal to bx omega dx. Now we will integrate it with the proper limits. Now let's suppose we have to calculate the EMF. We have to calculate the EMF of this rod between this endpoint and this endpoint. It means we have to calculate between A and B, right? We'll integrate it from A to B. Now if we have to calculate the EMF between, let's suppose we have to calculate the EMF between D and B. We'll integrate it from D to B, right? So accordingly, we can use the integration here to calculate we can put the proper limits here to calculate the potential difference between any two endpoints of this rod, right? Now for this question, we have been asked the EMF induced between A and B. So we'll take the limits of x from A to B, right? So x is at a position of 0 and B is at a position of L. We'll just integrate from 0 to L, right? So from here, B and omega is a constant. It will be integral of x dx. That will give us the total EMF, right, from the limit 0 to L, right? So from here, x, the integration of x is x square upon 2. So we'll be getting p omega L square upon 2, right? So that will be equal to half of p L square omega, right? So this is the induced EMF between the ends of this rods, right? Now let's suppose if we have given, if I have to find the uh, induced EMF between D and P, right? So here in this case, we will be having integral of dV. That will be integral of from D to B, right? From D to B, right? So it will be Bx omega dx, right? Bx omega dx. Now between P and D and B, so D is situated, positioned at L by 2 position from this origin, right? And B is at a position of L, right? We'll integrate it from L by 2 to L, right? So we'll get P omega here, x square upon 2 with the limits L by 2 to L, right? So from here, we'll get the value. So we'll be getting the value here So it will be half B omega multiplied by L square minus L square upon 4, right? So the induced EMF will be 3 by 8 B L square omega, right? So this will be the induced EMF in that case, right? So it depends upon between which 2 points we're actually calculating the induced EMF. Then accordingly we will have to integrate. We will have to substitute the proper limits. With proper limits, we can calculate the induced EMF between any 2 points, right? Now let's move on to the question number 7, right? The question number 7 is a metallic conductor of length 1 meter rotates in a vertical plane, right? We have some metallic conductor, it of length 1 meter rotates in a vertical plane parallel to east-west direction, right? East-west direction, right? About one of its end with angular velocity of 5 radians per second if the horizontal component of Earth's magnetic field is 0.2 into 10 to the power minus 4 Tesla, then EMF induced between two ends of the conductor. It's actually the same question, right? It's actually the same question that is rotating, right? It's rotating with an angular velocity of omega, right? We have to find the induced EMF between the two ends. So we calculate the induced EMF between the two ends. That's half P L square omega, right? Between two ends, that's half P L square omega. Now we can substitute the proper values here to calculate the EMF, right? Now value of B is because of the Earth's magnetic field, that's 0.2 into 10 to the power minus 4. And the value length of this rod is 1, that will be 1 square, and the omega is 5 radians, right? That's 25, right? That's 25. So from here, we will have the value here equal to 0. That will be 10 to the power minus 5, right? Multiplied by 25, right? Or we can write it equal to 2.5 into 10 to the power minus 4. So this much of the EMF will be induced in this metallic conductor of length 1 meter, which is rotating east west with a velocity of angular velocity of 5 radians per second, right? Now let's move on to the another question. The magnetic flux through a coil perpendicular to its plane is varying according to the relation. So we have been given that the magnetic flux uh, through a coil perpendicular to its plane, it's actually varying as 5t cube plus 4t square plus 2t minus 5, right? Plus 2t minus 5, right? This much is the magnetic flux, right? Or this is the variation of the magnetic flux as a function of time, right? If the resistance of the coil is given as 5 ohm, then the induced current through the coil at time t equal to 2 seconds will be. So we have been given the resistance of this coil is given as 5 ohm. We have to find the current, right, at time t equal to 2 seconds. So we have to find the current at this point, right? Now what we'll be doing here is that we'll just find the induced EMF, right? We'll divide the induced EMF by the current, by the what we call as time, right? Or we can find the induced EMF, right? Dividing the induced EMF at time t equal to 2 seconds divided by the resistance will give us the current, right? So current is nothing, it will be whatever be the induced EMF upon the resistance, right? At a particular time, right? So induced EMF will be nothing, it will be magnitude of induced EMF, that will be T5 over Tt, that has to be equal to, we'll just differentiate this equation, right? That will be 5t cube plus 4t square plus 2t minus 5, right? That will be equal to, it will be 15t square, right? Plus 8t plus 2, right? Now, this is the induced EMF, right? Now we have to find the induced EMF at time t equal to 2 seconds. We can substitute the value of t here equal to 2 seconds. It will be, it has to be equal to 4 into 15, that will be 60, right? And this, it will be 16 here plus 2, right? It will be 78 volt, right? So this will be the amount of the induced EMF, right? In this coil at time t equal to 2 seconds, right? At time t equal to 2 seconds, right? So at this instant, what will be the current? The current will be nothing. It will be 78 upon the resistance. That's 5, right? That's equal to 5, right? So this much of the current will be flowing through the what we call as coil, right? Now talking about the total charge flow, right? We can also calculate the total charge flow, right? We can also calculate the total charge flow, right? The total charge flow, let's suppose if the induced EMF is actually d5 by dt upon r, right? D5 by dt upon r, right? So if the current, we can write it as, it's a variable current, that's dq over dt. We can write it as d5 over dt upon r, right? So from here, this and this will get cancelled, right? So if we integrate it on both sides, right? So between any two times, right? Let's suppose between T1 and T2, the flux is phi1 and phi2. The total charge flown will be that will be delta phi change in flux upon the resistance. It's a very important equation to calculate the total charge flown due to the induced EMF, right? So the total charge flown will be nothing. It is always equal to change in flux upon the resistance. It's a very important equation, right? Uh, Frequently, the questions are being asked with respect to the calculation of the total charge flown if the flux as a function of time is given. So what we'll be doing is that, let's suppose between time we are asked a question, what is the total charge flown between the time t1 and t2. What we'll do is that we'll just find the flux. We'll just find the flux change in flux, or we can find the flux at t1 and t2, find the change in flux between the two time intervals, right? So divide that change in flux with the resistance, we'll get the total charge flown during the given interval, right? So this is a very important equation to calculate the charge flown between the two given time intervals, right? So now let's move on to the another question, right? The question is that a constant magnetic field of 1 Tesla is applied in the region x greater than 0, right? A metallic circular ring of radius 1 meter is moving with a constant velocity of 1 meter per second, right, along the x-axis. At time t equal to 0, the center of O of the ring is at a distance of x equal to 0, minus 1 meter, right? What will be the value of the induced EMF in the ring at time t equal to 1 second, right? So it means that if the speed of the circular ring is 1 meter per second, so it must have traveled a 1 meter after 1 second, right? So after 1 second, we have to find the EMF. It means that before 1 second, this ring must have been at this position, right? At this position like this, because the radius of this so this would have been the position of this ring before it enters the magnetic field, right? Now you can see here the radius of this ring is also equal to 1 meter, right? So it has traveled a 1 meter distance. So it means that the center of the center of this ring must coincide with the line of this magnetic field, right? So it means that we have to find the induced EMF, right? So induced EMF will be nothing here. It will be so this will be the total length here, which will be having like a rod here, right? So it will be nothing. It will be BBL. So we can write the L here equal to 2R. So it will be B multiplied by V into 2R, right? So this will be the induced EMF, right? Value of B is given as 1 Tesla, and the velocity is 1 meter per second. The radius is also equal to 1. So it's nothing. 2 volts is the induced EMF, right? So induced EMF in 1 second will be equal to 2 volts, right? Or there is another way of calculating it, right? In first second, right? There is another way of calculating it. The another way is of calculating is that we can just calculate the change in flux upon the time interval, right? So the change in flux will be nothing. The initially there is no flux. Once it enters after 1 second, right? The final flux will be nothing. Since half of the circle will be within this magnetic field, right? So final flux will be equal to it will be initially the flux is 0. Final flux will be B into A, B dot A. That will be magnetic field is 1 Tesla into area. Area is nothing. It will be pi r square upon 2, right? Pi r square upon 2, right? So accordingly, you can find the flux, right? Pi r square upon 2, right? Or we can write not pi r square upon 2. What we can do here is that we have to write it in terms of the length as well, right? So it will be area of this since it's moving along this speed, right? So this will behave as a rod, right? This will behave as a rod. So once again, we can assume it to be a rod moving a velocity of v along this direction, and the EMF is induced across this rod. That's equal to plus 2 volts, right? So this is the question, right? This is the question. And this question we can do in this way, right? So BVL is the equation we'll be using for this question as well, right? Now let's move on to the another question. The self-induced EMF of a coil is 25 volts when the current in it is changed at uniform rate from 10 ampere to 25 ampere in 1 second. The change in energy of the inductance is, we know the energy stored in the inductor is nothing. It's given as half of Li square, right? Half of Li square, right? So the change in energy will be nothing. It will be half L, right? I final square minus I initial square, right? So this will be the change in energy, right? Now the current has changed from 25 to 10, but we do not know about the value of this L, right? We know that the induced EMF is nothing. It is L di by dt, right? L di by dt. right, in a coil, right? Now induced EMF is actually given as 25, right? 25, and the current here is the change of current here is 15 volts in time 1 second, right? So L has got the value of 5 upon 3, right? 5 upon 3 is the value of L. So 5 upon 3 Henry is the value of L. We can substitute the value of L here in this equation. That's 5 upon 3. Now the final current is 25. It will be 25 square minus 15 square. So this much will be the change in energy in this inductor when the current changed from 25 ampere to 10 ampere to 25 ampere, right? So it means the energy of this inductor will actually increase, right? So the change in energy here will be a positive change in energy, right? So with this question, we have almost finished all the concepts of the induction, right? Self-induction, right? So these are some of the important equations or important questions that we had to discuss, right? In order to cover the most of the concepts of your upcoming exam, JEE mains, right? So that's it for today. We'll be discussing the next lecture a day on Monday, right? We'll be starting with the electromagnetic. We'll be doing some of the questions of EMI, and then we'll be starting with the alternating current, right? So till then, take care and goodbye.